Hi, so this is a video editorial for the LeetCode weekly contest 509. I'd say this contest was actually of a relatively higher difficulty than usual, especially like Q4 also required some techniques. Q2 was nice as well, and Q3 I missed some observation, which is why it took me way longer than expected. Initially, I solved it some other way only, which I guess, but I'll explain. I resolved the third problem with the what I assume is the intended solution after I made the observation. So as always, I'll be going through the problems in the order which are presented like Q1 to Q4. And after this, I'll attach the live solve section where you can see how I approach the problems in the contest itself. And there you can also see like what I did for problem 3. So problem 1 was straightforward. I won't be spending much time here since it's a fairly easy 3-pointer. Basically, you just have to do what it's stated. Like a digit range for a number is defined as the maximum digit minus the minimum digit, the difference. So we have to find the sum of all numbers which have the max digit range. So like you can make a function for finding the digit range of a number, and then you can put the sum of the numbers of a specific digit range in a map, and then just return the max value stored in the map, right? There are other limitations as well. This was something which I found to be easy to implement, so I did this. Q2 was nice. I'd say harder than the usual Q2. Basically, we are given two strings s and t, and we can perform an operation where we can choose an index in s and replace it with any other character, Latin character a to z, and we need to return true if it's possible to make s a subsequence of t. So like if s were a subsequence of t, here we can see even without an operation we have c a t, right? So s is a complete subsequence of t, whereas here if we try forming a subsequence, we'll see we have p plane here, and then we have L here, and then A, nothing matches A, right? So yeah, my implementation, my idea here was basically in problems where we are given that one string has to be a subsequence of some other string. Let's say here S has to be a subsequence of T, right? So let's say we have some characters in T here, and we have S. We are trying to form this as we are trying to make S a subsequence of T. So in this approach, let's say we have some character X here. We have some character X. We are trying to find the next character which matches X in S, X in this T string. So let's say we have X present here, and let's say we also have X here. So it is it is always, what do we say, optimal to connect this X with the X which appears earlier in T, right? Because let's say we connected it to this X, we won't gain anything. In fact, there is also a possibility that we might lose a character, like let's say after X there were Y. So if we connected it to any later X, it is also possible that we can lose this Y, right? Which is not optimal. So hence, it can be proved that it is always optimal to connect to the earliest occurrence of a character, which has not been processed. So this was my main basis for my solution, and for which now we have to handle this. We can perform one operation, right? We can choose an index and make it any other character. So my idea for, one second. For problems like this where we can perform any one operation and we have to do some matching, my rule which I use is, let's say we are performing an operation here at some index I, right? So after the operation is performed at I, we have to ensure that this section matches the rest of their, like rest of whatever we wanted to match, and this section, these two can match independently. These two have to match independently. I may or may not match, because if it doesn't match, then we can perform the operation, right? So yeah, this was my idea for Q2. It was like fairly like a nuanced idea. First, you have to know or derive the greedy thing for matching with the earliest occurrence, and then you need to also implement this thing, the prefix suffix thing. So this was my implementation. My DP, I just made two arrays, DPL and DPR, where L is from the left, how much it's matching, and R is from the right. So here I'm just making the count of indices which can be matched at most, starting from, let's say, like one second. Let's say this is my string t, right? I'm at some index, let's say j. So this dplj contains how many indexes I can match in my S string without any replacement, like direct match, the greedy thing which I explained earlier. How many I can match from this direction in dpl and in dpr from this direction. And in this way, what I did was, if this plus this, I mean not this, if this plus this plus 1 is that greater than equal to the length of the string, right? That means that we this section is matched successfully, this section is matched successfully, and then we can make a replacement here to always match it to some middle section, and then we can always find the subsequence here. So this was my solution for Q2. I found this like fairly clean. I like the solution. Q3 was a problem which I spent the most amount of time on because I missed one observation. I'll be going through an intended solution only. If you want to view what I was coding during the contest, you can view the live solve section. Basically, I'll give an overview. The problem is basically that Alice and Bob, I'll just explain it in layman terms. Basically what we need to do is select a subarray, select any subarray L to R, select any k greater than 1, and then for every number in that subarray divisible by I, we add it, else we subtract it, right? And we have to maximize this, the sum. We have to maximize the sum of the thing where we are adding, and if in case there are clashes, we want the smaller k. And this line is the most important thing, by the way, in this problem. In case there are same sums, we want the smaller k, and at the end we multiply, we return the product of the max score difference and the value k, and we mod it 1 plus 7. So there are some clues in this problem, and they can, for the previous problem the constraints were 1e5. I mean the solution was linear, so it wouldn't matter anyways. Here we have nums length is less than equal to 1000, and the numbers itself are less than equal to 10 power 6. All right, yeah. So since basically an idea here was, my initial idea was, one second, what is this? Okay, no worries. My initial idea was that since we have this, right, the k, what we let's say we pick some arbitrary k, right? If we have some arbitrary k, this k will have to obviously be factored, right? If it's not a factor of any element in the subarray, then it won't contribute anything, since it will just add negatives. So in that case, we won't do anything. It's not optimal. But in case k is a factor, then like for the numbers it is a factor, we'll add the number, and for the numbers it is not a factor, we'll subtract the number, right? So let's say we have k is equal to 7, and we have 14, 21, and 8. So here we'll add 14, we'll add 21, and we'll subtract 8, right? If k is 7. Now my issue was during the contest, we have 10 power 6, right? And the number of actual factors till 10 power 6 is way too large. Like it will be, it's like a number less than 10 power 6 has, like I tested this during the contest, it has around 250 factors. And assuming even though this is a very high upper bound, assuming every number to be different or something, we can have 250 into n, assuming every number to be different. So we can have this many factors, right? And for every factor, if we do this, it can get costly. So instead of this, an observation we can make here is, we can see that the problem states that in case k clashes, in case the sum is same, we want the smaller value, the smaller factor. So the observation here is, let's say after k is equal to 7, we had a k is equal to 21 for this check, and let's say this for 42 instead, right? For k is equal to 21, we'd also have this, 42 would be plus, 21 would be plus, 21 would be plus, and 8 would be minus. So the result is same, but k is larger, and we don't want k to be larger, we want k to be smaller. This means that every factor which is coming after a prime factor, it would be, the result would be the sums added would be the same and lesser anyways, right? Since if its prime factor divides the number, then this number may or may not divide the number, right? Let's say we have some number p which can be decomposed into prime. We have some factor f. my bad, we have some factor f, which can be decomposed into primes p0, p1, p2, and so on, right? If f divides the number, then these are guaranteed to divide the number, right? Which means there will be more pluses here than minuses. But if it is not necessary that if just because its substituent prime can divide it a number, that does not mean that a factor which it founds later will divide the number as well. So in that case, since here both our sum will be greater and the prime factor will be smaller, it is always optimal to choose the primes. And for a number less than equal to 10 power 6, we only have, like, I think I did some checks, right? We only have 25 distinct primes. This is also a very large upper bound. We can assume, like, let's say we have 25 distinct primes for all numbers, 25 distinct prime factors for a number less than equal to 10 power 6. So now instead of this 250 into n, we have 25 into n. 25 into n. So this is also very high upper bound. We have approximately 25 n distinct prime factors, which is a very high upper bound. And for every prime factor, every distinct prime factor, we can do the check of this. And for this check, we can basically just convert the array into, for a prime factor, we know its contribution of a number, right? If it divides, it's plus, else it's minus. So basically, we want the max subarray sum here. So for that, we can use gradients to find that in O of n, so the total solution comes out to be 25n square, which is a way higher upper bound. The actual runtime is way lesser than this. So this is my implementation for finding the prime factorization of a number. You can use a SPF sieve, which works in, this one works in log n, this one, because I'm doing this optimization here. Now what we can do is we can insert, push back all of the prime factors in some array primes, and then we can sort and unique them to make it unique. You can also use a set here, but it will give a worse runtime, I can guarantee that. And then this is just like for, we can choose a prime and then we can do cadence on it. Initially, I'm choosing best as -1 because there is a case where, let's say, nothing divides it. That means there are no prime factors, right? Which means all elements are 1. In that case, obviously the best would be -1, and then k min would be 2 since we can't choose k as 1. So yeah, this is just regular cadence, and this is if the next result is better, we update the best thing and update k min, else we don't, because if it's same, we want the smaller k min. And then at the end, just return this. So yeah, this was Q3, which I liked. Probably my favorite problem this contest. Q4 was straightforward if you know a technique. Basically, we want to find the maximum subarray sum of, now this is a palindrome, right? Now initially I thought this would be way harder than I expected, but an observation here is all numbers are positive. If all numbers are positive, one second, okay. If all numbers are positive, that means, let's say we have some array, right? We have some array, and if all numbers are positive, that means if we want the maximum subarray sum, which includes this element, then it's just the largest subarray sum, right here. Obviously, in this case, it will be the entire array, but with the constraint we are given that the array has to be a palindrome, which means, like, if you want the largest subarray sum, which includes this element, it means it is the largest subarray centered at this element, which is a palindrome. And once we know the bounds of the palindrome, which means the length, then we can find the subarray sum using some prefix sum or whatever, and then just maximize the answer. So this was my overall idea. And how do we find the longest subarray, longest palindrome centered at a point? For that, there is a standard algorithm known as Manishers, which can pre-compute all the subarrays, longest palindromes centered at a subarray in O of n, amortized O of n, similar to like how KMP works and all. And after that, you can also query if L2R is a palindrome or whatnot, but that's not what was required here. So yeah, this was my idea. Basically, you can do this. This is the suffix sum. This is my manager build. I'll give you a glance of my manager code as well. So yeah, this was the template I used. I think I've solved some problems regarding this before, which is why I have this template. And yeah, here then at every index we assume it to be the odd center and even center. Odd center, even center is basically odd length palindrome or even length palindrome. Assuming that we get the longest length, we get its left and right ends, and then we just suffix sum and maximize the answer. So this was Q4. Way easier than Q3 in my opinion, since it's straightforward. And the only observation was the positive numbers one. Alright. So you can view the live solve section after this.
James trending song अर्ज किया है from Folk Studio भारत. Stream now on Spotify.
इंडिया में तो हम रहते हैं, पर उसे जानते कितना है? कभी सोचा वो कहानियां जो गलियों, मंदिरों और हिस्ट्री के पन्नों के पीछे छुपी हैं, उन्हें सुनना कैसा होगा? And that's where I take you. Hi, this is Rakesh Soni, creator and host of the podcast India Unveiled. और मैं आपको ले जाता हूँ उन स्टोरीज तक जो इंस्पायर करती हैं, हैरान करती हैं और कभी-कभी बस दिल छू लेती हैं. From forgotten revolutions to secrets of ancient India. हर एपिसोड एक नए सफर की शुरुआत है. So search India Unveiled on Spotify. Hit the follow button and start listening.
अबे यार, ADPR है ना. सारे चीज़ें बैन नहीं कर सकता, क्या करते हैं, करते हैं। Yeah, 1v6 भी काम होता है। ना ना ये गलत है, ये गलत है, ये गलत है, ओवरलैप भी गलत है। This has to be positive one, then another zero set of factor penalty. Next children.
Listen to all your favorite Talapati Vijay hits and groove along with us to Uppity Podal right now on Spotify.
I think I finally found the one. उससे मिलके पता चला कि मूड के भी moods होते हैं. जैसे when I'm thinking of our future together, I'm Delulu. और जब साथ में होते हैं, it's full on puppy love. I'm talking about Spotify mixes यार. मेरे हर mood के लिए playlist बना देता है. My soulmate for a reason.
For every mood, there's a Spotify mix waiting. Just add mix to your search to get a playlist made for you.
इसी में इतना टाइम लग गया, आई डोंट थिंक चलेगा भाई ये तो। 1.5 सेकंड इसमें तो नहीं लगना चाहिए।
Let's check out what's trending in India right now.
Over here, sir.
One selfie,
please. We love you.
Goat is the only star trending this season. All because of the Flipkart Goat Sale. Starting 4th July, Flipkart has goat deals on everything. And while you shop, tune in to the Flipkart Goat Playlist. Brought to you by Flipkart.
For the first time ever, Navan Sandhu and Thandani Oniwala come together on one massive Punjabi chartbuster. Kat Lagda. Listen on Spotify.
My bestie said no. My dog always growled at him. मेरी ही गलती थी जो मैंने उनकी बात नहीं सुनी. I mean, the signs were right there. हमारा Spotify blend score was 23%. 23. But it's cool. He's history now. Because I have a new date. And it's a 95% match.
Need a vibe check? Just create a blend with them. Click on the Create tab and get started.